This week we are going to do counting, and next week we are going to do probability. Okay, so the last 2 weeks, those are what we're going to do. Okay, and those things are like both part of the counting and probability section. They're very similar. They're almost identical, I would say. So after today's class, if you get through it well, then probability will be very easy. It will be a continuation. Okay, so today we're going to actually cover a lot of things. We're going to start with Venn diagrams, then counting with multiplication. We'll talk about what a factorial is, combinations and permutations, counting with casework, and counting with corrections. Okay. So Venn diagrams. Sometimes when you're doing counting, Venn diagrams are a good way to organize your ideas. Okay. So we have this example problem here. In the school, there are 2 languages. There's Spanish and French. 18 kids take Spanish, 8 kids take both, and 5 kids don't take any language. If there are 29 kids in the whole school, how many kids take French? This is a very small school, but so what are we going to do here? We have 2 categories, Spanish and French. So we can make a Venn diagram out of that. We have one category here, which is Spanish, and another category here, which is French. Okay, we have 8 kids are taking both, so we know 8 goes into here. But the problem is the region over here, that's the amount of students that only take Spanish, right? In total, the amount of kids that take Spanish is this entire circle, right? So the stuff right here, that's only the amount of students that only take Spanish, okay? So we know that the total is 18, so 10 kids, right? 18 minus 8, 10 kids take only Spanish. What else is there? Well, there are 29 kids in the whole school. Well, we can say that. Let me admit someone in. We know there are 29 kids in the whole school. So, but there are 5 kids who don't take any language. So that means 5 goes outside of the Venn diagram entirely. It doesn't even go in it, right? Because none of these kids are in Spanish or French. So 5 is out here. And we know that there's only one section left. And if we add all the numbers together in these regions, we get the total. So let's say this is x. So we got 10 plus 8 plus x plus 5 equals 29. Okay, so x is going to be, let me see, 6. All right, so that means 6 kids go into this category right here. So once we finished our Venn diagram, now I got to answer the question, how many kids take French? French, when it says this, how many kids take French, it means how many kids take French in total. We have to take everything in this circle, not just this area, right? Because these kids are also taking French. So how many kids are taking French in total? That's going to be 6 plus 8, 14. All right, so that's how you would use a Venn diagram to solve your counting problems. Because you could do this without a Venn diagram, but it would be a lot harder because you would have to juggle like which students are taking both and like all that stuff. So a Venn diagram is basically a tool you can use. So we have 2 problems here. First one is very similar to what I just did. And the last one is a little more difficult. Okay, so for these problems, oh, sorry, person in the chat. Okay, so for the first problem, we have two categories, right? We have physics and biology. P here, biology here. Okay, 3 kids are not taking anything. 24 kids in total, which means that there are 21 in the Venn diagram. All right, we have 20 kids taking physics, which means there are 20 kids in this entire region. So there are 20 in there, 8 in this. Okay, so what does this mean? Well, we can set both as x. If we set that as x, then we have 20 minus x over here and 8 minus x over here, right? Because there are 20 in total in this circle, and we subtract out the x. So if we add all 3 of these numbers together, we'll get 21. So 20 minus x plus 8 minus x equals 21. 28 minus x, because you can see these will cancel, equals 21. X equals 7. So there are 7 kids who are taking both. Okay. Next one, you could do it without a Venn diagram. This is one of the simpler problems. 3, 4, but not 5. Well, you could just find the number of 3 and 4s and then subtract out the number that has 5. How many positive integers less than 100 are divisible by 3 and 4? Well, that means it's divisible by 3 times 4, which means divisible by 12. Now we know that 100 divided by 12, well, that's going to be 8 with a remainder of something, right? So it's going to be 8. There are going to be 8 positive integers, multiples of 12 less than 100. So there are 8 here, and you've got to subtract out the amount that has 5 in them. Well, now you just got to find how many numbers, how many multiples of 60 are less than 100. Well, that's only 1. So you just do 8 minus 1, that's 7. Okay, so the reason this worked was because we could actually do a Venn diagram for this. We can do a triple Venn diagram. So we got 3, 4, and 5. Everything in the middle, this is the section where all 3 of them are. And when we want 3, 4, but not 5, we're looking for the number right here. In this region, let me highlight that. You're looking for a number right here, right? So we take the amount that's in 3, 4, and 5 down here, and we subtract that from the amount that's just 3 and 4, which is the red portion. Okay? 3, 4, and 5, that's just, there's one of them, because it's at 60. And then 3 and 4 together, we find the red. The red we have, well, we found that's 8, right? So in total, there's 8 in the red region, which means there's 7 here. So the reason this problem worked without the Venn diagram was because it was more simple. But the actual reason it actually worked is because if you do a Venn diagram, this is how the math would play out. Okay. Sometimes you're going to have to use triple Venn diagrams. That's just a heads up there. So now we're going to go on to counting with multiplication. This is one of the more common the counting strategies. So this is an example. You have 3 pants and 7 shirts. How many outfits can you wear today? Well, let's say that you first choose your pants. Well, you got three choices for pants. Let's say we have pant 1, pant 2, pant 3. All right. Look how I've drawn a tree diagram here. So for each pant that I choose, I have 7 options for shirts. 1, 2, 3, 4, 5, 6, 7. If I choose this one, I have the same amount of options. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. If we count the fingers here, that's the amount of outfits we can wear, right? Because we built a tree diagram out of this. So whenever we can count with multiplication, we can draw a tree diagram in which each case branches out of the other. So you can see here that in this, we have a group of 7. Here we have 7, and here we have 7, which means we have 3 7s. 3 times 7, 21. Okay? That's how you would multiply with multiplication. That's how you would count with multiplication. All right? So let's go on. First. Okay. Give you guys 4 minutes. How about 3 minutes? Let's see. For the second problem, you have to buy at least 2 types of food. So you can't just buy a main course without anything else, okay? Okay. First one, the answer is 3 times 6 times 2. Well, why? You can make a tree map out of it. Let's say we first choose the side dish. So we got 3 choices here, 6 main courses. So out of each side dish we choose, we have 6 main courses that can branch out of it. 1, 2, 3, 4, 5, 6. Move this out of the way. 1, 2, 3, 4, 5, 6. And for each main course, we have 2 desserts branching out of it. And that's too much to draw. So you can see that after the first stage, we got 3 branches. After the next stage, we multiplied by 6, right? So we got 18 branches now. And now each branch is going to make 2 more, make 1 more. It's going to double. So in this branch, we have 36. So we did multiply by 6 and then multiply by 2 to get to 36. Okay. Next one, you can't just multiply all 3 numbers together. You cannot buy a side dish and a dessert. So what does this mean? Well, the only 2 choices are you buy a main course and a side, or you buy a main course and a dessert. Okay, so we can consider those as separate cases. So if we just buy a main course and a side, then we got 5 times 3 options. If we just choose a main course and a dessert, we got 5 times 4 options. We add these together, 35. Okay, so now we got to do the factorial. The factorial is a very, very common application, common operation. It's like adding, subtracting, multiplying, and dividing. It's an operation. So what this does is the factorial, it takes an integer and we put an exclamation point next to it. Okay, that means n factorial. And what this means is that, we take n and we multiply that by every single integer that's less than it. Every single positive integer, okay? N times n minus 1, n minus 2, n minus 3, all the way down to 3 times 2 times 1. So that's the factorial. So for example, if we have 10 factorial, that's 10 times 9 times 8 times 7 times 6 times 5, 4 times 3 times 2 times 1. Okay? So that's the factorial. Any questions about that? So we got to know that before we go on to the next section. All right. So now we're going to go on to permutations and combinations. This is probably the hardest part of this whole class. Okay, so the first thing is permutations. What is a permutation? The definition is if we have different objects, how many ways can we arrange them in a line? How many orders are possible to arrange them in a line? So we've got, let's say we have n different objects, okay? Let's say they're all different, okay? These may look the same, but let's say this one is red, this one is orange, this one is green, this one is blue, this one is purple. So how many ways can we arrange them in a line? For example, if we have green, blue, orange, red, purple, that's an order. If we have blue, orange, green, red, purple, that's also an order. But there seems like there's a lot, right? And there is a lot. So we can't just manually write all of this out. So we got to use multiplication here. So imagine we have 5 spots we need to fill in. Okay. For the first spot, how many choices do we have? 5 choices. Right? This is just like choosing a side dish. Right? This is the first step when you're building your meal. What about the next spot? Well, we already used one of them. It's in here now. So we only got 4 spaces left. Right? Next one, 3 options left because we already used 2. Right? We could have used this one, but it doesn't matter. There's only 3 left. Right? And then now we've got 2. Now we got 1. Right? Once we've chosen all 4 of these, the last one goes in automatically. So this is a multiplication problem, right? It's just like choosing a side dish and then the main course and the dessert and then maybe your drink or something. So we're multiplying all these together. And you can see that this is actually 5 factorial. And this is why we use the factorial, because this is the answer to the problem in which we've got 5 different objects. How many ways can we arrange them in a line? So this is the permutation. So when we have n different objects, how many orders? N factorial orders for them in the line. Okay, this is one of the easier parts because it's just multiplication, right? It's just a different kind of multiplication problem. Okay, so this is a permutation. How many orders? N factorial. Any questions? Okay, so now we're going to go on to combinations, and this one is a lot harder. Okay, so let's say we have the different objects again. We got red, orange, green, blue, purple. But now I have a bag. Okay, I have a bag, and I want to put 3 of these in this bag. Right? How many combinations of colors can I have in the bag? Okay, so the first thing you might do is you might say, oh, there's 3 available spaces in the bag. How many spaces for the first one? 5. How many spaces for the second? 4. How many for the third? 3. And you multiply all those together. You'll say that's 60. But that's not right. Because all I said was I want to have a combination of 3. All right. If I have red in the first position, let's say I chose red, green, and purple. Okay. If I put red in the first, green in the second, and purple in the third position, that's the same combination as having red, purple, green. And the same combination as having red, purple, red, green. Right? So we've overcounted here, right? Because all of these are considered as different orders in 60, but they're all considered actually the same combination. So we've overcounted here. How do we fix that? We can fix that by saying how many different orders can we arrange these three colors in, right? Because the amount of orders we can arrange them in is how many ways we've overcounted, right? So for example, let's say we can actually write them out. RGP, RPG, GRP, GPR, and then we got PRG and PGR. So those are the 6 ways we can arrange these things in the bag, right? And we've overcounted them in this number, 60. So what do we do here? Well, for every single combination of 3 we choose, we're overcounting by 6. Because there's 6 ways to arrange them in the bag, and each of these different arrangements is counted as one combination in 60. Does everyone understand that? Even though these are all considered 1, we're only supposed to add 1 when we have R, G, and P. But in this number, we have it 6 times. So that's not good. So what do? We divide through by 6, right? Because we have 6 times as many as we actually want. So we just do 60 divided by 6, and we get 10. Okay, so this is the combination. How many? We have n different objects. Let's say we have k different objects. And we want to take a group of n out of it. And how many ways can we form a group of n? And that's the combination. And we just want to have them in a bag. We don't care about what order they're in. We just want to have these existing in our bag. Okay, so what exactly did we do here? Well, we start from k, which is 5, and we subtract it down n times. We did 5 times 4 times 3. That's 3 times, right? Because there's 3 spaces, right? But this was overcounting, and we had to divide by the amount of ways we could arrange these n objects. Well, how many ways can we arrange n objects? That's n factorial, right? So the formula for a combination is if we take the total, which is k, and we multiply it down by the integers n times. So you can see here, we started with k, we multiplied 3 times. We went down each time, 5 times 4 times 3, and we divided by n factorial in the end. Okay, does that make sense? So this is the formula for the combination. First of all, we take the amount of ways we can order them in the bag, but we care about the order here. We're caring about the order because we're considering all 6 of these as different combinations. But that's not right. They're all the same. So we have to divide through by the amount of ways we arrange them, which is n factorial. Okay, so we start from k, and we multiply with the integers down n times. 5 times 4 times 3, that's 3 times 3 integers we're multiplying together. Okay, so for example, if let's say we had 20 objects, okay, and I want to make a bag of 3 of them. Well, we got to start at 20, multiply down 3 times. 20, 19, 18, divide by 3 factorial. Okay, which is going to be 3 times 2 times 1. As you can see here, this is how we do it. So the way we write a combination is we do this. This is how we write a combination. We say, this is how we write 20, choose 3. This number basically means how many ways can we choose 3 objects out of 20 different objects? We want to have a bag of them. We don't care about their order. And this is the way we notate it. This is the way we write it. Okay. So when somebody says, what is 20 choose 3? This is how it's going to be written. 20 and then 3 at the bottom. Right? We can't have 3 choose 20. That's illegal because we can't have 20 out of 3. Right? There's only 3 that exist. Okay, so 20 choose 3, that's how you would write it. And this is equal to this number, right? So we take 20 and we subtract down 3 times and we divide it by 3 factorial. Any questions? All right. Problems here? Okay, so the first one is pretty easy. This is a permutation. We have 6 factorial ways, and if you were to multiply it out, that would be 720. Okay. The way this works is that we have 6 positions here. First position, we have 6 choices. That kid is already in, so the next position, we have 5 choices left. And then it goes 4, 3, 2, 1. And this is just a multiplication problem. And that's it. Okay. So the next one, 10 kids running for class board. There's 1 position for president and another position for vice president. They have to be held by different people. How many ways can these be assigned? We've got 1 position for president, 1 position for vice president. First one, we've got 10 choices, right? There are 10 kids running. Any of them can be the president. The next choice, the vice president, well, one of the kids is already the president. Then that kid cannot be the vice president as well. So the next one, we've only got 9 choices left. And that's it. We just multiply 10 times 9 and we get 90. Any questions? All right. Now, the first problem here is very similar to the problem we just did. This one's different, though. Can you see why? Okay. So the first one is different. Because we have 3 available spaces in the student council, but they're all the exact same, right? It's not like there's a president and a vice president and like a secretary of state. They're all the same. So this means if we assign, let's say, John, Bob, and Alex in this order, this is the exact same thing as assigning Bob, John, and Alex, like this. Right? So if we were to just do 10 times 9 times 8, that wouldn't be right because we're overcounting these. Right? And how many ways can we arrange John, Bob, and Alex? 6, right? 3 factorial. So we divide through by 3 factorial, that'll be 120. So this is actually a combination problem. As you can see how this worked out, this is actually 10 choose 3. Because what we're actually doing is we're just choosing 3 people and push them into a bag, for example. The student council is the bag. And we're just putting them in the bag. We don't care about how they're arranged in there. As long as these people are in there, that's it. So we're going to use 10 choose 3. Next one is, this basically tells you got to have a choose. So it's a combination problem. So you're allowed 2 friends to bring to Disneyland, and there are 7 friends to choose from, but Tom and Jerry are twins and cannot be separated. So this means you cannot choose Tom and some other kid. You cannot choose Jerry and some other kid. If you have Tom in it, Jerry has to be part of that group as well. Okay. So this is the only way you can have Tom or Jerry going with you to Disneyland, right? Otherwise, they're not going to be able to go. So this is the only way you can have Tom and Jerry to go. So now all you need to do is to consider the last 5. There's 5 left. And how many combinations can you choose from 5 of these? Well, that's 5 choose 2. We do 5 times 4. We multiply 2 numbers. Divide by 2 factorial, which is just 2 times 1. 10. Okay. So we've got 10 ways to choose from the 5 remaining. And there's 1 way to choose Tom and Jerry. So you've got 10 plus 1, 11. Okay. And one thing I forgot to mention earlier, if you were ever to consider, let's say 5 choose 0, right? This would be 1. Why? Because how many ways are there to choose 0 objects? 1, right? You just don't choose anything. That's the only way you could do it. So 5 choose 0 is 1, and 0 factorial is also 1. Okay, so that's just how it works. Okay. I'm going to do counting with casework. So sometimes we're going to have to divide up a problem into casework. And what this means is we're dividing it into cases. And each case is like a different case of the problem. And we're basically splitting a problem up into different counting problems. So we could have case 1, case 2, case 3. And if we evaluate how many possibilities in each case and we add them together, we got the total number of possibilities. Okay, so some problems you're going to have to use cases. You're basically splitting the problem up into multiple counting problems, and you're adding all the results together. So I'm going to show you how to do this with one example problem. So the first problem here, I have a bookshelf, and I want to arrange some books on it from left to right. All the books are unique. I have 2 math, 3 history, and 2 science. The math need to be placed next to each other. The math books cannot be placed next to each other, and the science must be placed next to each other. How many ways can we arrange them? Well, we're going to use casework here. So the first case, we can just consider the math textbooks and see how they're going to have to be placed. Well, we got 1, 2. I mean, in total, we got 9. We got 7. 1, 2, 3, 4, 5, 6, 7. Okay, so how can we place the math textbooks? We have math. So if the first math textbook is here, we've got 1, 2, 3, 4, 5 for the other math textbook, right? So right now we're just figuring out which spots we'll reserve for math textbooks. Right, we're like reserving it. Like when you go to the maybe the park or the Great America, you're going to reserve a parking spot for you. So this is we're just reserving these for the math textbooks. We're going to say these have to be math textbooks. Okay. We don't care about which math textbook is on the right or the left just yet. Okay. So all we're doing here is we're finding how many ways can we put these math textbooks on the shelf? How can we reserve the spots for math textbooks? So that was the first case. The first case was where this math textbook is on the left. But the problem is, if we do this case, the science textbooks must be next to each other. then we can't have science. So that's a roadblock we're going to encounter if we do it this way. So we're going to have to take those out later. That's going to get really, really complicated. I don't want to do that. So what do? Whenever we have a situation where we have two things must be next to each other, we'll just consider them as one object, right? Because wherever they go, they're going to have to be next to each other, right? And in the end, all we need to do is multiply by 2 because these sign textbooks can be arranged in 2 ways inside their block, right? But right now, all I can do is I can consider them as one block, one book. So what I can do is actually, if we consider the science textbooks as one book, we've just got 6 books. 1, 2, 3, 4, 5, 6. Okay. So now our counting is going to change, right? So we've got, we're doing the math textbooks again. This is how we're going to reserve them. We can have them like this. If the first textbook is on here, then the second textbook can be in 4 positions. What about the next one? Well, we're going to move the first textbook there. We're going to have 1, 2, 3. If we put it here, we got 1, 2. We're just going to have 4 plus 3 plus 2 plus 1. And that's going to be 10. So there's 10 ways to reserve the math textbooks. So now we've got math textbooks in position. These 2 spots have to be for math. So now we can put the science textbook anywhere we want, right? We have 3 spots left. We can just put, so we just put science here. So we got 10 ways to put the math down, 1 way to put the science down, well, not 1, 3 ways. I actually erased 1. We have 4 ways actually. I erased the spot, so you got to be careful here. 4. Let's say the science is in position. Now we got 3 history textbooks left. We just got to arrange them like that. So we got 3 factorial. Okay. So, but now all we did was we reserved these for math textbooks, and we reserved this for the science. But inside the math textbooks, we can arrange them in 2 ways. We could have the first math textbook on the left, and we could have it on the right. So there, we have to multiply this by 2 for the math and 2 for the science, because inside the block of science, these 2 books can be arranged left and right as well. So this is actually the final answer. 3 factorial is 3 times 2, so 10 times 4. 3 factorial, that's 6 times 2 times 2. Okay. So that's how you would use casework. And this is actually another strategy in which you use reservations. You're reserving a spot for the math textbooks. You're reserving a spot for the science. Okay. So now let's do this problem. 5 friends getting in the canoe. Okay. All right, so this problem, I'm gonna write 5 spots for these guys. Jonathan has to be at the front, so that's a given. Only one choice for that, right? Only one position that Jonathan can be in. So now Jen and Matilda do not want to sit next to each other. So this is just like the math textbooks we talked about earlier. They don't want to be next to each other. So we're going to reserve spots for Jen and Matilda. We got to reserve them. Okay, we're going to say these are the spots that they can sit in. Okay, so we can have this pair, or this pair, right? Otherwise, they're going to be next to each other. So we got 3 choices to reserve the spots for Jane and Matilda. All we're doing here is we're saying these are the spots you guys can sit in. That's it, right? We're reserving these spots for them. Now, we got to arrange them in these spots, right? Either Jane can be in the front or Matilda could be in the back. So there are 2 ways to arrange them in these spots. 2 ways to arrange Jane and Matilda in these reserved spots, right? So there are 3 spots we can reserve for them. And then we got to mix them around in those spots, which means 2 choices for each spot. So 3 times 2. Now we got to consider the 2 other friends who don't care about anything. They have to sit in the 2 remaining spots, right? And all we need to do is arrange them either front or back. Let's say that there's Alex and John. And John can sit in the front or Alex can sit in the front. So there are 2 ways for that. Okay. And that's it. After that, we got everyone in position. All you need to do is multiply 1 by everything, which doesn't really do anything actually. And this will equal 12. And 12 ways to sit in the canoe. And for a problem like this, if you don't really know how to count it mathematically, you could just write it out, write all the possibilities. It might take longer, but if you really have no idea, manual counting is viable, okay? But you can make a lot of mistakes while you do it, okay? So there's one more topic I did not talk about today, but that's fine. I'll do that next time.